Hello, class. Today is this is the first lecture of the morning. I have made sure that all of the things are set up correctly. And we are going to talk about centroids of composite areas. That basically means that we're going to have various different types of areas. Some are going to be added, some are going to be subtracted. And in fact, let's just look at the mathematics involved. And if you remember, originally I said that, let's just use the x centroid. I said that the x centroid times the total area of the cross-sectional area, whatever it is, a circle, a triangle, a circle with a triangle in it, whatever, is going to be equal to the integral of x dA, right? And so that is our equation if we want to find out, and that's what we used in the last lecture to find out what the equation for the centroid was of a triangle, and we derived both of those. Now, what we want to do is we want to just extend that a little bit further for centroids of composite bodies. And what we're going to say is that the total centroid, I'm going to put total centroid for a composite body, is just going to be the sum, and I'm actually going to put some things here. I equals 1 to n, and that would be standard for all Riemann products. I'm not going to write that all the time, but I will, write it sometimes. So that would be x sub c I times the individual area of that cross-sectional area divided by AI all the way up. So we've got the centroid times the area divided by the area. And doesn't that look a lot like this? In fact, if we wanted to find out the area for like a triangle or whatever, didn't I actually use the identity that this was just x dA divided by a total? So that's what I did, with that original definition of what a centroid is going to be. And all I've done is really extend that out here for composite bodies. And instead of saying, well, I'm just gonna use the calculus, now I'm just using a Riemann sum to do the same thing. And so I want to look at just two examples of this, and just see what, how we would put together the individual areas, either put them together, taking them away. So the first one that I'm going to do is just going to be a composite cross-sectional area. This is nothing that's all that interesting or anything that you're going to see in the future. But let's see, 1, 2, 3. So that would be, let's see, 1, 2, 3. And how wide is that? That is 4 wide. So there's 4. There's 3. There we go. So that's the top of it. And then 1, 2, 3, 4, 5, 6. 6 down. All right. And so here we have a composite body that's got a triangle and a rectangle. But what I'm going to do is I'm going to add an extra thing in there. Let me just see. 1, 2, 3. 3 up. It's going to be my center, and then 1 around there. So I'm going to remove area. I mean, if I had to draw this as like a thin plane, a planar, just a slab of metal, if you want to think of it that way, and I made this thing into something that looked like that. I'm just trying to three-dimensionalize this for you, right? And it would look something like that if it was just a flat object. So it would have a triangle at the top. And in fact, I wouldn't really have this piece here at all. There's nothing connecting it. It's all one piece. We probably cut it all out of a piece of steel, and then we just bored a hole out of the center of it, right? I'm going to actually say that this is going to be a, I could work in centimeters. Why don't I just do that? Let's say that this is just a small piece of steel that we've machined up. It's 4 centimeters, and then it's going to be 9 centimeters long, but the distance from here to here is going to be 6 centimeters. And then the distance from here to here is going to be 3 centimeters. Does everybody see that? So that's the the item. Now, this really is just an area. I just was giving it some thickness so that you could see that this is all additive, subtractive. So when we're trying to figure out what the X and Y centroids are of this, I think everybody can see what the X centroid of this is. Let me just draw that there because it's symmetric. And this is something that I wanted to bring up too. If we have something that's symmetric about a certain axis, then we know that the centroid has to fall along that axis. So if I was looking for the centroid right here, this would be my centroid for the x-axis. I think everybody can see that, right? It would be at 2 centimeters would be my centroid for the x-axis. Let's just formalize that though, so that we know that that is going to be the case. And the first thing that we want to do is we want to go to our book, right? Want to go to the textbook that you've got, and inside the textbook you've got in the back leaf, or someplace in the textbook too, you have this, Centroids of Common Shapes of Areas and Lines, right? And the top of this is all centroids of areas, and then the bottom of this is centroids of line segments. And the centroids of line segments are different than the centroids of areas because you're basically placing all of the emphasis on just the line, just this. I'll talk more about that in a little while, centroids of line segments. And of course, centroids of line segments are different than centroids of cross-sectional areas. Now, what I want to do is I'm going to make this point right here 0, 0, right? So we're going to have an x-axis that's coming up here, and then we're going to have our y-axis that's going up there, and we're going to find both the x and the y centroid relative to that Cartesian coordinate system that I have laid down on this cross-sectional area. I really should even remove this three-dimensionalization here, but I'm just saying, look, this would work just as well, finding the centroid if it was or the center of gravity, if it was a flat piece like that anyway. Okay, well, let's look at what these three are. We got a rectangle, a circle, and a triangle. So the first thing I want to do is call the rectangle object 1, right? That's going to be area 1. I'll make the triangle area 2. And I'll make the circle area 3. And of course, we're going to subtract the circle because the circle, isn't there, right? So let's just go back to our original equation that we've got here, that the overall total centroid of that composite body is going to be the sum of all the individual centroids times their cross-sectional area divided by the total. In fact, the total, summing all of those up on bottom. All right, so let's do that. So X total for that cross-sectional area is going to be the individual centroid times the area of that. So let's do the first one first. So that's going to be the rectangle that we have here, right? I think everybody can see that the rectangle that we have here is going to be 6 centimeters by 4 centimeters. And if I look at the X for that, it's going to be at 2 centimeters in, right? So it's going to be 2 centimeters. That's the centroid for the rectangle, all right? So 2 centimeters in the X direction times the cross-sectional area for the rectangle, which would be 24 square centimeters. All right, now let's add the next one because it said we're supposed to sum all of these up, right? So the next one that I've got, my triangle, I think everybody can see that the triangle, right, is 1/3 up, but the actual, since it's an isosceles triangle, the centroid, the x-centroid for it's going to be right in the middle of that isosceles triangle. It'll be 1/3 of the way up. When we do y, we'll have to take that in consideration. But right now, as far as x goes, isn't this symmetrical about that? So the centroid in the x direction has to lie along that line. So again, we've got 2 centimeters, right? And now the triangle, which is going to be 3 by 4, that's 12 divided by 2 is 6. So 6 square centimeters, right? Now what I want to do is I want to subtract off this because I've cut this hole out, haven't I? I've cut this hole out of the block that I have here, or the cross-sectional area. So I'm going to have to subtract that. Again, that's going to be 2 centimeters. And then what's the area of that circle? Well, the radius is 1. So it's pi r squared. So it's pi times 1 squared. So that would be 3.1416. I'm just going to put 6 square centimeters because I'm running out of room, right? And then over that, because that is the first part of that Riemann sum, right? We've multiplied the top together, but now we've got to add up the individual ones from the bottom. So the first area that we have is 24 square centimeters. The second area that we have that we're adding in there is going to be 6 square centimeters. And then the third area that we're taking out of there is going to be minus 3.1416 square centimeters. And again, I use, instead of 3.14159, I'm just using the 3.1416 square centimeters, you know, to do that. All right. You know what? Did I change that to? I use 0.5. Well, you know, I don't know. I put that thing in there. I had done this a little bit differently back then. So what have I got here? Just a second. Let me check something. Hi, class. Sorry about that, but I had an important note from my brother that came text. You know, I've got older parents, and there's a lot going on with them. So, you know, every once in a while, I have to break out of lecture mode to take care of things like that too. So anyway, let's get back to this. As everybody can see, I've got basically the same area down here. 24 plus 6, that's 30. 30 minus 3.14 gives me 26.85, something like that, right? And then on top, you can see that I've really added those. I could actually take this to the next step and take the 2 centimeters out of each of those and just have that and then just cross them out. And they would both cancel out, you know, wouldn't they? I think that everybody can see that too. If I did want to put that together, why don't I just give you a number? Of course, centimeters times centimeters squared give me centimeters cubed. So I would have 48 centimeters cubed plus 12 centimeters cubed minus 6.283 centimeters cubed. And that is going to give me 53.72. So X bar, left the thing off too long, is going to be 53.72 centimeters cubed on top. And then I think we can all see what's going on bottom. This is going to be 26.85 something. So 26.85 square centimeters. And that should give us 2 centimeters. And of course, that's what we know it is because we can see from the symmetry of the area around 2 centimeters, it's going to be 2 centimeters. And that's what it works out to be too. So that's our, that is our X. Instead of doing it, since it's all in one, let's just use the orange. So that is going to be our X bar. We call it X bar. That's a colloquial name for the X centroid, and Y bar, of course, is the colloquial name for the Y centroid. That's what I want to work on now. You know, the X centroid, like I say, was very obvious, and of course you want to do the very obvious one first, and then you want to do the less obvious one second to make sure that you've done the whole procedure and the protocol and everything is down. So let's find Y bar. So if I wanted to do the same thing I did, so Y bar, the total Y bar for the entire composite area is going to be the original Y bar to the area. So if you look at this, you can see for the rectangle, right, Y bar for the rectangle is going to be half the way up the rectangle, right? So it'll be right at there, and that's going to be at 3 high, 1, 2, 3, because the rectangle is 6 high. So that's going to be at 3 centimeters, you know, 3 centimeters up, times the area of the rectangle, and we know the area of the rectangle is 24 square centimeters. Now let's do the second one. Let's do the triangle. Now we know for the triangle, this is going to be at centroid, right? So where is that centroid? Let's see, that's 6 plus 1. So that would be 7 centimeters. That's the centroid of the triangular piece times the area of the triangular piece. And of course, we've got 3 times 4 divided by 2, and that's going to give me 6 centimeters, 6 square centimeters, just like it was above. And then we want to subtract off the one here. And of course, that's at 3 centimeters, right? And then what is the area of that circle? Well, the radius is 1. So 1 times pi r squared. R squared is 1 squared, and then 3.14. So it's going to be 3.1416. I'll just continue using that. Square centimeters, right? And so we had to subtract that one off because that's a hole that is cut out of that. I always like to use this whole thing so you can see where, you know, this is a negative, of course, because I'm cutting that out of there, right? And down here, the areas have to be the -2, 24 square centimeters, that's additive, plus 6 square centimeters, that's additive because pow, pow, they're added. And then I'm taking this away. So, you know, I shouldn't, I don't know why I put the plus there. It should, of course, be a minus. That was the whole point I was trying to make there. It's a minus, and it's 3.1416 square centimeters. All right. So this one isn't quite as straightforward as the symmetrical one for the X centroid, but the Y centroid can be figured out just as easily. Let's just do that. 3 times 24 plus 7 times 6 plus 3 times pi, and that all equals 123.42. 123.42. And what are my units? Centimeters cubed. Now here, since I've got centimeters, cubed and centimeters squared, I just use centimeters because I'm only using that unit the entire, way through. So it doesn't really bother me too much to stay in centimeters since that's all we've been working in. And when I look down here, I'm going to get the same thing, 26.85, but I'm just going to add, put these into my calculator, get something that's a little more accurate, maybe 24 plus 6 plus pi 30, oh wait, excuse me, 30 minus pi 26.858. Let's put that 8 there. 26.858 square centimeters. So Y bar for that composite area that we've got there, really I should probably leave, let's do the Y bar over here because I'm going to leave this area to draw another one. Let me just mark that out for a second. So Y bar for the first one, for this one that we're working on, the only one that we're working on right now, is going to be 123.42 divided by 26.858, and that gives me 4.595. So really, we could say it's 4.60. 4.60, and that is a significant figure, so I want to put a line across the top of it to let the next engineer that's going to look over my work to know that that was a significant figure. All right. Now, that sort of ends the analysis that we did, excuse me, on that composite figure that I've got up here. I want to work with a more boy, I can actually draw this. Yeah, I should have left room here. In fact, that's what I'm gonna do. I'm gonna take this. I'm gonna see if I can get rid of that line. Boy, I love the little thing that I've devised there. Let's make this a little bit longer. I think we'll still have plenty of room for it, though. I'm gonna draw it like this now. And then I'm gonna, well, let's see, how can I do this? 1, 2, 1, 2, 3, then down, over, down, over, down, like that. And what I'm going to do here is I'm going to bring that out a little bit further. Let's see, 1, 2, 3, 4, 5. Nope, that was right where I wanted it to be. All right, and then what I'm going to do is I'm going to draw this, right? I'm going to draw that. And I'm going to tell you that that has an equation of y equals 3x to the 1/2, right? Then I'm going to give you some other things here. This distance here is going to be 25 centimeters. And then each of these distances here are going to be 5 centimeters. So I'm just going to draw little arrows to those locations to show those are 5 centimeters. Now also up here, keeping to scale, each of these is also 5 centimeters. So let me just write 5 centimeters here and then just draw arrows to all 3 of those heights. So all 3 of those heights are 5 centimeters too. Now that's a composite area that, it's, we've got several different things here. Let me just break them up. I'm going to make this into a rectangle. I'm going to make this into a rectangle, and I'm going to make this into actually a square, but you know, it's a subset of a rectangle. Now, what are we going to do with this here? Right? We know this is 3x to the 1/2. Well, that's no good. But you know, if y equals 3x to the 1/2, and we were to make this, right, y, and then this, x. So this is our 0, 0 right here. If we were going to make that, you know, if y equals 3x squared, let's just write that down. Y equals 3x, did I say squared? I meant to the 1/2. You know, can't we look at that the other way? Can't we say that that would be y divided by 3 squared, right? Because y is going to come into the bottom here. So it'd be y divided by 3. And then if I'm solving for x, that would be y divided by 3. You know, really, isn't that the same as if we had y squared divided by 3 squared? Does everybody see what I'm doing there? So that's really 1/9. So if I have 1/9, that's 0.111. So 0.1111, it's an ever repeating thing, y squared. I think I've given 4 significant digits there, so that should be fine, right? So y equals 3x to the 1/2. Bring the 3 over, square both sides, that gives me x, and that gives me x equals 0.111 y squared. And where is that going to be? Before we do any of this, what we should do is we should just look and see, you know, where is that going to be? That's going to be down here, isn't it? This one is going to be right here. This one's going to be right there, and this one's going to be right there. So if we're looking at the y centroids for each one of these, right, we can just add them up like this. We'd have to figure this one out, and we'll have to go back to this. And on this, what we do is we look at this. Now you can see in your book that this, right, is my y equals kx squared, but I can turn that around into x equals ky squared, and we can figure out what the what it is. So I'm going to refer you back. I can't really move it up here because it wouldn't be, there's no autofocus. You can only see it down here. But you can see that this one is 3a over 4, and this one is 3h over 10. And I'm just going to refer to this because this is in your book, and you're required to be reading your book. So I think that's all fine. So what we want to do is we want to look at all of these composite areas now, and we want to find out both their x and y centroids. I'm just going to shade this one in so we can see they're all areas and not line segments. And you know, we're going to break it up into individual parts. And I'm just going to take my orange here. So that's going to be a break, that'll be a break, that'll be a break, and that will be a break, right? So we have 4 different areas. I'm going to call this area 1, 2, 3, and area 4. I don't know if you can see those. That's written with a relatively thin pen, but I think that you can make those out. And so this is going to be a little more difficult than the one that we had originally, but we can figure out what the area is under this curve too, can't we? Because this is going up to 15 right here, and it's 25 right here. So y equals 3x to the 1/2. I can always, you know, figure out what that is. We could do it either way. It's still going to be the exact same area. But we're really trying to find the area. So for area of number 1, to figure out what that is, we're really looking at the area under the curve. So it's just going to be the integral of 3x to the 1/2. And we want to go from 0 to 25 centimeters, right? dx. So, did I start that? Yes. Yes, I did, and I can't believe that I only have that much time left. But whatever, we've started this, and I want to finish it. So 3x to the 1/2, we can take the 3 out of there, and then it's just the integral of x to the 1/2 dx, and that's going to be x to the 3/2 divided by 3/2, evaluated now between 0 and 25 centimeters, right? And that would give us our full thing. So x over 3/2. So this is going to be 2/3 times x to the 3/2. So 2/3 times x to the 3/2 evaluated from 25 centimeters to 0 centimeters. Okay. And that would be, let's just plug in. So 25 centimeters to the 3/2 times 2/3 equals, wait a second, so I'll give it to you in centimeters. Hey, wait a second, just a second. Hi class, I'm back again. And this is what, you know, teaching in person, I wouldn't have had this problem. I wouldn't have dropped this constant, but you can see that I've got the 3 there. And when I came down here, I thought, and this is an engineer's intuition too, I was looking at it as, that does not seem right. That does not seem right. And of course, what we've got here is, I forgot to carry that 3 through the equation, right? And that's what I need here. That should be a 3 times that, and there should be a 3 times that too, right? Because I carried the 3. I took it outside of the integral and I forgot to carry it through. It's a problem that happens. Let's just throw a 3 out in front of there too. And what that gives us is 0.25. 0.250 square centimeters. I hope that that's correct, because that does not seem correct. Oh, wait a second. No. I use 0.2. So this isn't square centimeters. This would be, in fact, why don't I do it in both? That would be square meters. Sorry about that. So it is 0.250 square meters, but let's do this. So if I had 25 times 1.5 to the 1.5 times 2, oops, wait, forgot to turn it on. Sorry about that. 25 taken to the 1.5, and then the 3's cancel out, so times 2, and that gives me 250 square centimeters. Now, square centimeters, let's see how we would change that. Wouldn't we divide that by 10,000? So divided by 10,000, that gives me 0.02. 0.02. Well, why did I get that? Because if I did it in meters, that would have been 0.25 x to the y 1.5 times 2. That gives me 0.25. So what am I doing wrong here? Just a second. I'm going back. I had this all done out. Just proofing it. Okay, I'm back. Basically, the way that I'm looking at this is y equals 3x squared, but I was trying to, you know, do this so that I could actually work out the area down here. I am just going to cut my losses here. There is something obviously here that I'm missing, but what I'm going to do is I'm just going to figure out what the area of the spandrel is, the parabolic spandrel. I'm just going to use the other direction so that I can use this equation right here, x equals 0.111 y squared, and that's still going to give me the thing, because now I'm just going to go from 0 to 15 centimeters, so 0 to 15 centimeters, and then I can just use this, which is going to be 0.1111 y squared dy, and just lining things up. It's still going to give me exact same thing. So what this really gives me then is 0.1111 ad infinitum y cubed over 3, let's extend that, and then evaluated from 15 centimeters to 0 centimeters. All right, let me see if I've got all that, y cubed over 3, yes. And so when we find the area of the spandrel, then it is going to be, let's just plug that in there, 15 to the third divided by 3 times 0.11111, and I think I get 125 square centimeters. All right. I'm sorry I didn't, you know, I obviously left a 2 or something out in there or something, but anyway, this is just as easy. That's the area of the spandrel. Now, what we want to do is we want to take our sheet here that looks at the spandrel, and everybody can see that that's sort of how the spandrel is laid out there, but we've got it backwards, don't we? Because this is going to be the base of that spandrel, right, which we have it reversed on the sheet that we've got here. Can everybody see that this line right here is really going to be this line right here, right? So let's call this small a, and small a would be there, and then if this were small b, then small b would be there, right? So we've got it backwards because this is kx squared and this is x to the 1/2. So if we did it backwards, it would be that way. Anyway, if we look then and see what this distance is, that's going to be 3h over 10. So in here, right, that's 3h over 10. This being h right here, right? So 3 times 25 centimeters divided by 10. 3 times 25 centimeters divided by 10. I think everyone can see 775, so that's 7.5 centimeters. Right? Let's wait a second. 3 times 25 divided by 10. Yes, and that would be off. That would be off this long side here, so 7.5. So we can really say that the first, if we wanted to find the first one for that, that x bar would be 25, 25 minus 7.5, and that gives us 17.5 centimeters, right, for that first one. We could also look at it this one, but we can now look at 2, 3, 4, and put those in there too. So if this distance is 25 and this is 5, so that would be 2.5. So for number 2, x bar equals 27.5 centimeters, and A2 is going to be equal to 15 centimeters by 5 centimeters. So 75 square centimeters. For number 3, I would have the 5, so that's 30 plus 2.5. So x3 is going to be 32.5 centimeters. And its area is going to be, well, 1/2 of 75, or 50 square centimeters. And then for number 4, x bar for 4 will be, let's see, 25, 30, 35, 37.5 centimeters. And then the area for number 4 is just going to be 1/3, so that would be 25 square centimeters. So that's all of the work that we've got for that. I think this video has gone a little long, so I'm going to finish this part, because this is a relatively complex composite body, in the next lecture, and then we're also going to go on to do the theorems of Pappus and Guldinus. All right. Not sure how long this is, but I'm sure that it's over now. All right.